Relational algebra. Let's go back to our architecture of a database management system for some context. You can see we're working our way up from the bottom quite nicely. We've made it all the way through all the storage issues, and we're finally getting to the parts that have to do with query processing. We're beginning today with the definitions of the relational operators that we will execute to evaluate queries. And coming soon, we'll also look at the implementations of these operators. But today is going to be definitional. We're going to get the semantics of those operators defined and understood. What would be nice to do, since we just have one hole between the top of our stack here and our current context, is to talk a bit about how we connect the SQL layer down to the relational operators. So let's overview that at a high level. So starting with a familiar SQL query like this one over sailors and boats, we're going to have the parser translated into a form that the optimizer is going to want to manipulate. Now the optimizer is not going to get it in this form right away, but the optimizer is going to work with operations that look like these. And these are in a language called the relational algebra, which is what we're going to learn today. That relational algebra expression can be represented as a tree of operators like this. It's the same expression, just laid out as a tree. And we call this sometimes a logical query plan. It's a strategy for executing the query expressed in terms of these operators, which don't have a physical implementation yet, but are a logical representation of what we want to do and in what order. Now the optimizer itself is actually going to produce a physical optimized query plan, which for every operator in this tree is going to generate an actual algorithm to pump data up through these edges in a sort of data flow fashion through these operations called iterators that are going to produce the output. So we're going to learn all this stuff on the lower right later on when we talk about query execution. Today we're going to focus on the relational algebra and what it means. Note that that SQL and the relational algebra have interesting differences. SQL is a declarative expression of the query result. It says, here's what I want in the output. Relational algebra, on the other hand, is an operational description of a computation. It says, in rough terms, take this table and that table and combine them in this way, and then apply this operator to them, and so on. So it's somewhat operational. It tells you what order of operations to take, although the operations it takes are on big objects. They're on entire tables, not on individual tuples or cells in memory. But it is an operational description, and it's enough to help us get the system come up with a concrete physical query plan to execute that relational algebra. Okay, let's return ourselves to SQL. Here's an SQL query, and remember the system features that we liked about SQL. It's declarative. You say what you want, not how to get it. And then the system, namely the query optimizer, is going to figure out the how. And the foundation of the SQL language is in a formal query language known as the relational calculus. So a little background on the history of formal relational query languages. The relational calculus, which as we said is the basis for SQL, is a declarative language. It describes the results of a computation, and it's based in first-order logic. Here's an example of a variation of the relational calculus called the tuple relational calculus. We won't learn this in this class, but it's pretty easy to read if you know first-order logic. This says, find me all S such that S is in sailors, and there exists some R in reserves, where R.SAD equals S.SAD, and R.BID equals 103. It's quite a lot like SQL when you read it out loud. The relational algebra, on the other hand, is an algebra. It's based on sets, so it comes from a different branch of mathematics. It's an algebra, not a logic. And it provides an operational description of the transformations that we want to do. It says what transformations to execute and in what order. Now the question is, are these two languages equivalent? And can we translate from one to the other? And these were problems that people thought about back in the 1960s. Specifically, a guy named Ted Codd was the person at IBM who pioneered this area. He's often known as the founder of the relational model. And his key theorem, Codd's theorem, established an equivalence in expressivity between the relational calculus and the relational algebra. He showed that all the queries you can say in the calculus can be expressed in the algebra, and all the operations that you could compose in the algebra can be expressed with an equivalent expression in the calculus. And for this work, Codd was awarded the Turing Award in 1981. Why is this such an important result? Why does it merit a Turing Award? Well, it connects this declarative representation of queries with an operational description. It allows us to imagine a world where people ask for things from computers, and the computers figure out algorithms to implement them, which, is actually pretty forward-looking. It's a very AI-like view of how to program computers. His theorem's also constructive. It shows how to translate calculus to algebra. And so it gives us that first step in a long line of research that got us to compile SQL into actual execution strategies, like we'll learn about in this class.